Did you find out what was happening when we looked at the Routh table for this polynomial s cube plus 6s square plus 4s plus 5? We wrote down the odd part of it, its coefficients first, 1, 4, and then the even part 6, 5, and then by doing this peculiar operation, pivot element into this minus this into this divided by pivot, we got the entry 19 by 6. That means it corresponds to the linear polynomial 19 by 6 into s. And lastly, we got just the constant polynomial 5. And my question was, from the two polynomials s cube plus 4s, which corresponds to the first row, and 6s squared plus 5s, which corresponds to the second row, we obtained the third row, which corresponds to the polynomial 19 by 6 into s. Now, what is the relationship between these polynomials? What you are doing to construct the array or table, I hope it is clear, but what is its significance in terms of polynomials? In fact, we do these things on the entries of the table because they correspond to some polynomials. The whole algorithm or the whole idea is really based on looking at a set of polynomials. It is done in a compact fashion by not writing down the powers of s, provided you do it in a systematic way, and then only computing the coefficients of the polynomials. Now, I hope some of you have found out the answer, and the answer is the following. Here is the first row polynomial s cube plus 4s. Here is the second row, which also corresponds to another polynomial 6s squared plus 5s. The original polynomial was of degree 3, so we wrote down the odd part first and then we wrote down the even part. Now, suppose I were to divide this odd part by the even part, then what would be the quotient and what would be the remainder? Now, first of all, because of the fact that this is an odd polynomial and this is an even polynomial, and the degree of this polynomial is just 1 less than the degree of the other polynomial. You remember from school algebra or arithmetic, this polynomial s cube plus 4, 6, which is being divided, is called what? It is called the dividend polynomial. That is the polynomial which is being divided. The polynomial which divides it is called what? It is called the divisor polynomial. So, the divisor polynomial has degree 2, the dividend polynomial has degree 3. So, the difference of degree is 1. As a result, quotient will be s to the 1. This is called the quotient. What I am going to work out is called the quotient. This quotient is going to have a power of s equal to exactly 1, and what will be the coefficient of this power? Well, I have s cube here, I have 6s square here, so to cancel off this s cube I have to write 1 by 6 s here. So, if I do that 1 by 6 s to the 1, and then how does the division algorithm go? Well, I multiply this by the divisor and then write down the product. So, I will have s cube here plus I will write this now as 5s into 1 by 6s. I am deliberately going to write this as 5 into 1 by 6 into s. Now, we subtract this. So, the s cube power cancels out, and that is what was expected, and what remains is what? 4 minus 5 into 1 by 6 s. There is no constant term. So, notice what has happened. There is an odd polynomial which is divided by an even polynomial whose degree is just 1 less than the odd polynomial. The quotient is just s with some multiplier, that is, it is a polynomial of the kind k into s. In this case, this k is 1 by 6, and the remainder is an odd polynomial. The remainder, when the odd polynomial is divided by an even polynomial, is an odd polynomial. Now, look at the table that we had and let us compare and see what we get. So, here on the table I have 1, 4, 6, 5, and the quotient is, the next entry is 19 by 6, and what did I do? I did 6 into 4 minus 1 into 5 divided by 6, 6 into 4 minus 5 into 1 divided by 6, and that was that 19 by 6. Now, do you see this 6 times 4 minus 5 times 1 here? Almost. What I have here is 4 minus 5 into 1 by 6. Now, this can be rewritten as 6 into 4 minus 5 into 1 divided by 6. So, the entry that we are writing here, 19 by 6, obtained by following that rule, is actually the coefficient of the remainder polynomial. This polynomial which remains after the division operation is called the remainder polynomial. And so what is really happening is that when we divide the polynomial which corresponds to the first row by the polynomial corresponding to the second row, the remainder polynomial is the next row. What about the quotient? The quotient, as we saw, is s to the 1 or s multiplied by some coefficient, and what is this coefficient is 1 by 6. And do you see 1 by 6 here somewhere? Almost. Here is 1 here and here is 6. So this 1 divided by the pivot element is the coefficient of the quotient polynomial, and in this case 1 and 6 have the same sign, and therefore the coefficient of the quotient, which is 1 by 6, is positive. So the Routh table construction involves, not explicitly but implicitly, starting with a pair of polynomials and then carrying out this division remainder operation repeatedly. Let us take one more example to illustrate this. The example will be a little longer and you should try to carry it out as I am doing it now, so that you would have understood it a little better by trying it out yourself. In the previous example we had only a cubic polynomial s to the 3, so there were two rows that we started off with, s cube and s square, and there were only two more rows to be filled up, s to the 1 and s to the 0, or a linear polynomial and a constant polynomial. The first polynomial was odd, the second polynomial was even, then by division we obtained a remainder which was odd. The next step was this s square polynomial, that is corresponding to the s square row, 6s square plus 5s, was divided by 19 by ss to obtain a quotient 5. Let me do that explicitly. So I will carry it out here. I have that 19 by 6 into s is the polynomial which divides 6s square plus 5. What is the quotient and what is the remainder? Let us try it out here. 6s square plus 5 is the polynomial corresponding to the second row. Now that is divided by the polynomial corresponding to the third row, which is 19 by 6 into s. So what is the quotient? The quotient will be, of course, here is s square and here is s, so the quotient will be s to the power 1, and what will it be multiplied by? It will be multiplied by 6 divided by 19 by 6, and therefore when I multiply this into this, I will get 6s squared, so that is going to cancel off with the 6 square, and then what will I get? Nothing, and therefore when I subtract, the remainder is 5, and this remainder is indeed what we had in our table. 19 by 6 into 5 minus nothing divided by 19 by 6 was 5, and that is indeed the quotient that we have here. So the Routh table construction involves doing compactly polynomial division and repeated, in the sense, start with a pair of polynomials, get a remainder, then use the last two rows polynomials, get a remainder, and keep on doing this till you reach the constant polynomial. When you reach the constant polynomial, it is not necessary to go any further, because a constant polynomial will always divide any polynomial. For example, here I have a constant polynomial 5 and I write down a polynomial, let us say s square plus 10s plus 6. My claim is that I can find a quotient such that the remainder will be 0, and of course this is very obvious. I just take the quotient which is 1/5 of this polynomial and then the remainder will be 0. So there is no point in doing this last step when the remainder is going to be 0, and therefore it is not done. We stop with the constant polynomial. So let us take now one more example. Let the polynomial be s to the 6 plus 2s to the 5 plus 3s to the 4 plus 4s to the 3 plus 5s squared plus 6s plus 7. I have just chosen a simple example with coefficients 1, 2, 3, 4, 5, 6, 7, and it is a polynomial of degree 6. Now you should try to construct the Routh table yourself. I will get you started with the first two steps, and then you should carry it on without looking at what I am doing. So here is the first row. The highest degree term is s to the 6. Notice that the polynomial is monic, and I told you that you can always make the polynomial monic. So I have s to the 6, then so coefficient is 1, then the s power 4 is 3, s square is 5, and s to the 0 is 7. So I have the four numbers 1, 3, 5, 7. What I have done is I have written down compactly the polynomial s to the 6. How do I know it is s to the 6? Because there are 4 entries, but better still there is this s to the 6 here. So s6 plus 3 s4 plus 5s square plus 7. This is an even polynomial. Next, and this is the even part of the given polynomial. Next, I write down the odd part, starting with s to the 5. I have 2, then I have 4, then I have 6. So what is this polynomial? It's an odd polynomial. It is given by s to the 5 multiplied by 2 plus 4 into s cube plus 6 into s. So I have broken the original polynomial into its even and odd parts. That step is easy. The next step is now involves this division of polynomial, but instead of doing it by actually writing down the dividend, the divisor, then working out the quotient step by step, we do it compactly by doing that particular operation, which involves starting with the pivot element and then doing some things crosswise. So don't look at what I am doing, do it yourself. I am going to do it myself. Have you finished the s to the 4 row? The next row, that is, how did I get it? 2 into 3, 6 minus 4 into 1. So the difference is 2, divide by the pivot element, that's 1. Next, 2 into 5, that's 10 minus 6 into 1. So the difference is 4, 4 divided by the pivot element is 2. 2 into 7 minus what? Minus nothing, because there is no entry here. The polynomial is s to the 1 is the last entry. So there is nothing here, don't put a 0. 2 into 7 minus nothing, or there is nothing to subtract, divided by the pivot element 2. So that gives me 7. So I have obtained now an even polynomial. In the third row, the polynomial is s to the 4 plus 2s square plus 7. And what is the significance of all of this? This polynomial, which corresponds to the first row, when divided by the second row polynomial, first row is an even polynomial, second row is an odd polynomial, leaves a remainder which is an even polynomial. 1, 2, 7 are the coefficients. And what is the quotient? The quotient is simply 1 divided by 2. So if I write the quotient on this side, the quotient is 1/2 of s, or 1 divided by 2 into s. Where does that 1 by 2 come from? It is this 1 divided by this 2, that is the quotient. Now we will continue. So I will write down the s cube entries. Once again, don't look at what I am doing, do it yourself. Have you finished? It is an s cube polynomial now, starting with s cube, and the entries are 0 and minus 8. How did I obtain that? Now there is a new pivot element. Now we forget about the first row, we look at only the last 2 rows that we have obtained. So this is the pivot element now. So this multiplied by 4, and that is 4, minus this product, which is also 4. So the difference is 0 divided by the pivot element 1, therefore I write a 0 here. And next, this one crosswise is 6 minus this one crosswise is 14. So 6 minus 14 is minus 8, and that I am dividing by 1, and I get minus 8. And what is it that I have here now? I have an odd polynomial. And what is the polynomial? It is 0 into s cube minus 8 into s. Now there is something which has happened here which will not allow us to go further. In fact, the usual approach is to say that when this happens, we know immediately that our polynomial is not good, it is a bad polynomial. What has happened is now I have got a 0 here. What about the quotient? When this polynomial is divided by this polynomial, what is the quotient? The quotient is 2 divided by 1 into s. So the quotient is again a power of s, the first power of s. Now what is going to happen? I have an even polynomial which is s to the 4 plus 2s square plus 7, and the next polynomial is minus 8 into s. The degree of the even polynomial is 4, the degree of the odd polynomial however is not 3, but it is 1. Therefore the quotient is not going to be s to the 1, but it is going to be something different. And therefore when this happens, you have to use some other rule or some other device to proceed further. So this 0 here in the first entry of a row gives you a warning, not that your calculations are wrong, but that the polynomial that you are working with is a bad polynomial. And what did I mean by a bad polynomial, or what is a good polynomial? From the point of view of stability, meaning that if I look at the 0 input response when the initial state is not 0, that 0 input response as time increases will go to 0. If that is the case, then we call the system a good system, and for that the characteristic polynomial should be such that all of its roots have negative real parts. So that is what was meant by stability, and that is what I mean by a good polynomial. If a polynomial has even one root which is not in the strict left half plane, that is one root which is not negative real, or it does not have a negative real part, it could be 0, it could be purely imaginary, it could be positive real number, or it could be in the right half of the complex plane. All those polynomials are bad polynomials in the sense that the 0 input response will not go to 0 as t tends to infinity, and we do not want the 0 input response either to remain constant at some non-zero value, or to keep on oscillating, or to keep on growing, because that is the case when the system response will keep on increasing, and therefore somewhere or the other something will happen. A fuse may blow, or the system will be no longer in the linear region of operation, so all our analysis is just no longer applicable. We are looking essentially for a test to find out whether a polynomial is good, and of course for what values of the gain Ka the polynomial is good, that is what we are looking at. So the moment you get a 0 as a pivot element for the next operation, that is a warning that you have got a bad polynomial. Now in such a case one can do something and proceed further in a somewhat different way, and then get some information out of all this. But if you just want to check that the polynomial is bad, then you can stop here and say that the polynomial has at least one root which is not in the strict left half plane. So if that is the question that you are interested in, then it is answered right away. Now there are techniques, and I will not go into details, and the Routh table construction or the Routh theorem or the algorithm, as I told you, is about 120 years old. Naturally a lot of people have looked at it, and situations like this have also been looked at, and this has been discussed in many journals. Not all of it appears in textbooks, so your textbook may tell you some way out or something else to be done when you get a situation like this, but we will not have enough time to discuss all those details. But such a case in general is called a singular case, and a case when this does not happen is then called a regular case. So unfortunately with this polynomial now we are ending up with a singular case, and what is bad is from the point of view of polynomials the degree difference is not 1 but it is 3, and from the point of view of the algorithm there is an immediate problem, because now my pivot element is 0, and if I am going to divide by the pivot element, then I will be committing the sin of dividing by 0, and dividing by 0 is meaningless. I can write infinity, but that does not help me at all. As you can see from here, for example, 0 into 2 plus 8, so that is plus 8 divided by 0, so should I write plus infinity or minus infinity? And similarly 0 into 7 minus nothing divided by 0, should I write 7, or it is 0 by 0, so I should write it as some other number. There is no point in just proceeding arbitrarily, and then that does not guarantee that you will get the correct result. So let us leave this singular case here. It is an indication that the polynomial is bad, and if that is all we are interested in, we stop. There are techniques of proceeding further by doing some things, but I am not going to discuss them right now. So we have encountered a singular case, but the earlier example was a regular case, because with this polynomial we could go all the way till the end without any problem. There was no 0 encountered in the first column, pivot element was not 0, so there was no problem, one could go ahead and get the answer. Now let me take one more example which we had looked at earlier, but we had not carried out the Routh table construction. Now that is s to the 4 plus 3s cube plus 6s square plus 12s plus 8. This is the polynomial. Same algorithm to be used. So start with s to the 4, the coefficients are 1, 6, 8, next row s cube, 3, 12, there is no entry here, so I am putting a dash. Now the next step, the division process, this is the pivot, 3 times 6 is 18 minus 12, so difference is 6 divided by 3 is 2, 3 times 8 is 24 minus nothing divided by 3 is 8. No problem so far, I have not encountered a 0 here, so I can continue one more step. I write down s to the 1. Now this is the new pivot element, mind you. Now and we look at the last two rows that we have obtained. So 2 into 12 is 24 minus 8 into 3 is 24. The difference is 0 divided by 2 is 0. Now we have encountered the same trouble. A pivot element has become 0. So the polynomial is bad. The polynomial is bad. The original polynomial is bad. It will have at least one root which is not in the left half plane, strict left half plane. Now this therefore looks like a singular case. Now is it any different from the previous singular case where we had a 0 as a pivot element? On the face of it, no, but there is a difference because this is a polynomial which is odd degree 1 and therefore it has to have only one term. So this entire polynomial is 0. So although this is a 0 1 0 here, the conclusion is that this whole polynomial is 0, whereas in the previous case I had a polynomial which was not identically 0, not all the coefficients were 0, one coefficient was 0 but the other coefficient was not 0. So this polynomial is not 0 but it is 0 into s cube minus 8 into s. So the whole polynomial is not 0 but only a part of it, namely the leading coefficient which should have been s cube, is missing. The coefficient is 0. So this is a different singular case. This is also a singular case because it is not regular, but it is a different kind of singular case. And we can take one more example to see what is happening, where you can really see that the remainder polynomial is an identically 0 polynomial, and it is not difficult to construct examples of this kind, and therefore I will tell you how you construct an example of this kind so that you will realize how textbooks or authors who write papers think of these examples. If I ask you to write a polynomial, maybe you will write like I wrote s to the 6 plus 5 1 s to the 5 plus etc., some such, and what is going to happen to it you just do not know beforehand. But now I will construct a polynomial and I will show you what is going to happen and why it is going to happen. So I am going to construct the polynomial like this. I am going to write down a polynomial s squared plus 1. Now what do we know about this polynomial s squared plus 1? Well, we have looked at such things earlier. What are the roots of this polynomial? Plus minus j. So they are on the j omega axis, imaginary axis. They are not in the left half plane. Let me multiply it by s square plus 2. What are the roots of this? Plus minus j root 2. So now I have a product of two polynomials and all the roots of it are on the imaginary axis. There is no root in the left half plane. Now let me change it further by multiplying by s plus 1. Now what is happening? There is one root which is in the left half plane. So there are four roots which are on the j omega axis and there is one root which is in the left half plane. Now let me work out this polynomial. What are all the coefficients? And that is not very difficult to do here. I have s to the 4 plus 3s square plus 2 multiplied by s plus 1, and therefore what do I get? I will get s to the 5 plus what is the s4 term? S to the 4 plus what is the s cube term? S to the 4 is coming from here. S cube term is 3s cube. What is the s square term? S square term is 3s square. What is the s term? S term is 2s and the constant term is 2. So this is the polynomial that I will get. Let me check. This is s4 plus 3s square plus 2 into s plus 1. So s to the 5 plus s to the 4 plus 3s cube plus 3s square plus 2s plus 2. So that is the polynomial. Now let us start our Routh table. So s to the 5 I will get 1 3 2. S to the 4 I will get 1 3 2. This is a polynomial s to the 5 plus 3s cube plus 2s. This is the polynomial s fourth plus 3s squared plus 2. This is odd polynomial, this is even polynomial. I carry out the division operation. So this is s to the 3. This is the pivot element. What do I get? This times this is 0. I am not finished because there is this operation also to be done. This times this is 2 minus that is 0, so I get 0. So the next polynomial, not only is this entry 0, but the other entry is also 0. So the entire polynomial is 0. In fact, what is happening is, if you check for yourself, this odd polynomial which is s to the 5 plus 3s cube plus 2s square, which is being divided by the even polynomial s to the 4 plus 3s square plus 2. This is such that when I divide it by this, there is a quotient. The quotient is of course 1 divided by 1 into s, namely s, but the remainder is identically 0. or I can say the remainder should have been a polynomial of degree 3 for me to proceed further, but it is a polynomial whose coefficients are both 0, and therefore I cannot proceed any further. But this was different from the earlier singular case where I encountered only a pivot element which was 0, the other element was not 0. The pivot element is 0, the other element was not 0. This is the difference between this case and the case that I am looking at where the entire polynomial is 0. So this is a singular case which is different from the earlier ones. Now such a singular case indicates what we see here, that there are roots on the imaginary axis or on the j omega axis. So a singular case where one says the entire row is zeros or vanishes, then this implies or this indicates that the original polynomial has roots on the j omega axis. It has roots on the j omega axis, and in fact you can find out what those roots are, or at least make some progress towards finding out what those roots are. What you do is, when you encounter this row of zeros, look at the previous row. The previous row is this polynomial s to the 4 plus 3s square plus 2. Then this is a polynomial which is a factor of the original polynomial, and then you factorize this polynomial, and then we look at its roots. In this case it is not difficult to factorize this polynomial, so the roots will be simply s squared plus 1 and s squared plus 2, the factors, therefore the roots will be plus minus j1 and plus minus j root 2. Now unfortunately it is not as simple as that, so it is not really correct to say that when the entire row vanishes there are roots on the j omega axis. It has happened in this case, but it is possible to construct an example where this will not happen. In fact, it is possible to construct an example where the Routh array construction cannot get started at all, and I will take a very simple example which is important because it indicates a particular very special situation. Let us look at the polynomial s to the 4 plus 1. Of course, I told you earlier that if a coefficient is 0 or if there is a change of sign in the set of coefficients, then the polynomial is already bad. So we know that this polynomial is bad, and so if we really wanted only that much information, we will stop. But suppose I try to apply the Routh algorithm to it, what will I get? Start off with s to the 4, no problem, leading coefficient is 1, s squared term is 0, constant term is 1. What about the s cube polynomial? Well, there isn't any. This polynomial does not have any odd part, or the odd part is really the 0 polynomial, 0 into s cube plus 0 into s. So I am stuck, pivot element is 0, but it is the second case, singular case, or the singular case where the entire row is 0. Now look at the previous row, it is s to the 4 plus 1. Now what are the roots of this polynomial s to the 4 plus 1? A little bit of thinking will enable you to find out the roots. Put s squared equal to z, squared equal to z, we are making a change of variables. Then what does s to the 4 plus 1 become? It becomes z square plus 1. So when is z square plus 1 equal to 0? When z equal to plus minus j. So here is the complex plane, here is plus j and here is minus j. So the roots of the polynomial z square plus 1 are plus j and minus j, but our polynomial is a polynomial in s fourth plus 1 and not z square plus 1, and we have this relationship between s and z, s square equal to z. So s is a square root of z, so I have to take the square root of j, and in fact when I take a square root, there is not one but there are always two square roots in general, or always really. Similarly for minus j, I have to take the square root of minus j. How do you take the square root of j? Convert it into the polar form. In the polar form, j is the same as e raised to j pi by 2, and therefore one of the square roots of j will be e raised to j pi by 2 divided by 2, or e raised to j pi by 4. And where is that complex number e raised to j pi by 4? Well, it is located here. If I draw a unit circle around the origin, then this is the root which is square root of j. So this is one of the roots of the polynomial, therefore its negative will also be a root, and then from minus j we get two more roots like this, and so this polynomial s to the 4 plus 1 will have 4 roots which are located like this in the 4 quadrants, and they are located in a symmetric way, and such a symmetry is called quadrantal symmetry. Because there is a symmetry that involves roots lying symmetrically in the 4 quadrants, it is called quadrantal symmetry. So here is an example of a polynomial where the Routh algorithm results in a row which is identically 0 and not just the leading coefficient of a row, the pivot element or a few elements 0, the entire row is 0, still there are no roots on the j omega axis, whereas in the earlier case that I took, here the entire row was 0 and the roots of the polynomial were on the j omega axis, and indeed they were the roots of the polynomial s to the 4 plus 3s square plus 2. So this result that I wrote is not really correct. An entire row vanishes does not imply that there are roots necessarily on the j omega axis, but what is true is that if an entire row vanishes, then the roots which are maybe on the j omega axis will be factors of this polynomial, which is the last non-zero polynomial. So this result is not true. However, the result, as I have stated in the modified form, is true, and this rule can be used to find out the intersections with the j omega axis. In this second singular case, where you have a row, entire row which is 0, again there are techniques which have been devised to proceed further to get some other information out of the Routh table. In principle, with the simple rule that cross product divide by the pivot element, I cannot proceed any further. I have to give up. I get, of course, the information that the polynomial is bad. I get that information because I cannot continue. I encountered the singular case. The moment you have a singular case, the conclusion is that the polynomial is bad. But can I get some information other than the polynomial being bad? The answer is yes, provided I do something further. Now, what further is to be done when you have a situation like this, again will require quite a bit of looking into. Your textbook probably has some indication, but as I told you, this is a subject which has been studied for a long time, so there are quite a few techniques, and some of the results which are mentioned in the textbooks or some of the techniques which are given in the textbook may also fail. So this problem is not as simple as it looks, but we really are not interested in full problem of given a polynomial, say something about its roots. Our main problem was the root locus method, where we wanted to find out intersections with the j omega axis, and how does the Routh algorithm give us a way of finding out the intersections. That is what we are interested in. So let's get back to our original problem and try to apply this Routh array technique to that problem. So here was the pole 0 diagram, which I have been looking at for quite some time now. There are 3 poles, minus 1, minus 3, minus 4. There are 2 zeros, plus 2 and minus 2. So what is the characteristic polynomial? The characteristic polynomial, if you remember, was GD HD, that is the denominator of GH plus the gain Ka into Gn Hn. Let me call it P of S. This is the characteristic polynomial. In this case, the denominator, there are only 3 poles, so I have s plus 1 into s plus 3 into s plus 4 plus Ka. In the numerator, I have s plus 2 and s minus 2. So s plus 2, s minus 2, because there are 2 zeros. These correspond to the zeros, these correspond to the poles. So the polynomial corresponding to the pole part plus Ka, this gain of the amplifier whose effect we are trying to find out, multiplied by the polynomial corresponding to the zeros. So let me expand this out then. This is s cube plus, as I told you earlier, 4 plus 3 plus 1, so 8s square, plus 3 times 1 is 3, plus 4 times 3, 12 plus 3, 15 plus 4, so 19s, plus 4 into 3 into 1 plus 12, plus Ka into s square minus 4. So collecting coefficient, then I have s cube plus, and I have here 8s squared and I have Ka s squared, so 8 plus Ka into s squared plus 19s is not affected, plus however 12 minus 4 Ka. So this is the characteristic polynomial, and as you can see, it depends on Ka. We would like to find out where are the roots of this polynomial, or really we would like to find out for what values of Ka will Ps be bad, and if possible, for what values of Ka will Ps have roots on the j omega axis. This is the problem we are trying to investigate. For what values of Ka will the polynomial become bad, So, we know that the roots will no longer be all of them in the left half plane, at least one root will not be in the left half plane. And secondly, for what values of Ka will the polynomial have roots on the j omega axis, and if possible we can find out the location of the roots. So, let us proceed further. So, with the table construction, then I start with my s cube row, because the degree of the polynomial is 3. So, s cube, the coefficients are 1 and 19, s square I have 8 plus Ka, and the second entry is 12 minus 4 times Ka. This is an odd polynomial, so s cube plus 19s. This is an even polynomial, 8 plus Ka into s square plus 12 minus 4 Ka. Next step, this is the pivot element, s to the 1 power. So, I will get only one entry, and that entry will be what? This into this minus this into this divided by the pivot. Now, when I do this multiplied by this, I am going to divide by the pivot. So, I need not carry out the multiplication and then divide by the pivot. So, I can write down here directly 19, this is the term here, minus this product 12 minus 4 Ka divided by 8 plus Ka. This is the whole coefficient. Okay. Now, can I proceed further? Well, I can if this coefficient is not 0. So, the question that we have to ask is this coefficient 0? Can this coefficient become equal to 0? So, that is the question I am going to ask. I am going to give you a little bit of time to work out whether this coefficient can become equal to 0. I am going to do the calculation, you should also do the calculation side by side. Okay, here are the calculations. 19 minus 12 minus 4 Ka divided by 8 plus Ka, is it equal to 0? That is the question that we are asking. Now, carrying out the product operation, then 19 into 8 plus Ka should be equal to 12 minus 4 Ka, and therefore collecting the coefficients we will get 23 Ka should be equal to this 12 minus 152 or minus 140, and therefore the answer is this will be equal to 0 for a particular value of Ka, namely Ka equal to minus 140 divided by 23, minus 140 divided by 23. This is a negative value of K, and we are only looking at positive values of the gain K. We are not looking at any negative values of the gain K. So, this pivot element will not become 0. It will not become 0 for a positive value of K. Of course, what this is will depend on what Ka you have chosen, but for positive values of Ka, this coefficient will not be 0. Now, the question is then, can I proceed further? Yes, I can. If this pivot element is not 0, then I can proceed further. And what is the next row now? I have the 2 rows that I have obtained. From that I have to obtain the next row. This is my pivot element. This multiplied by this entry minus what? Minus nothing, because in this there is only s to the 1 power. So, this multiplied by this divided by the pivot will give me simply 12 minus 4 Ka. Alright. So, I will write down the Routh table. I will call this K prime because it is a complicated expression. So, my Routh array is going to look like s cube is 119, s square is 8 plus Ka, 12 minus 4 Ka, s to the 1 is this K prime, and this K prime is not 0, and in fact this K prime is positive, as you can verify. S to the 0 is however given by 12 minus 4 Ka, right. You can check that this K prime is actually positive for Ka which is positive, because if you cross multiply you have this 19 Ka plus 152, on the other side you have 12 minus 4 Ka, and therefore the left hand side will be greater than the right hand side, and therefore K prime will be positive. Alright. Now, of course, I have gone all the way up to s to the 0, so I have not encountered any singular case. However, some things can happen. This coefficient can become 0, Yes, when will it become 0? 12 minus 4Ka equal to 0 will become 0 when Ka is equal to 3. Of course, there is no need to go further, but the moment I have a 0 here, this means that for Ka equal to 3, my polynomial will be bad. Will my characteristic polynomial be actually bad? Well, look at the original polynomial and substitute Ka equal to 3 and see what you get. The polynomial was s cube plus 8 plus Ka s square. Ka is 3, so plus 11 s square plus 19s plus 12 minus 4 Ka. Now, what is 12 minus 4 Ka in this case? It is 0. And therefore, the polynomial is actually s cube plus 11s square plus 19s, or it is s multiplied by s squared plus 11s plus 19. And so, there is a root which is at the origin, or the origin is a root for this value of Ka equal to 3. Now, of course, this is exactly what we had guessed earlier when we were looking at the root locus method. When we use the root locus method, we argued that there is a portion of the root locus lying on this part of the real axis, and therefore, there will be a root which will be at the origin for some value of Ka. Now, by using the Routh table, we have obtained it in a different manner altogether, and that has involved a pivot element becoming equal to 0, or equally well the previous row becoming equal to 0. Now, is there anything more than that we can conclude from this? The answer is yes. Remember what I told you earlier, that if the table is completed, that is, if you don't involve, if there are no hurdles involved, if you don't get stuck because of a pivot element becoming 0 or an entire row becoming 0, then once the table is completed, you can look at the first column of the table, and this is the first column of the table. And then what is it that you have to look for? You have to look for change in sign of the entries as you go from top to bottom. So, I start with the top. This is 1, it is positive. Second entry is 8 plus Ka. Remember, we are looking only at positive Ka. So, this is positive. The third entry is K prime. I told you, and we agreed that for Ka greater than 0, K prime is also positive. So, this is positive. What about the last entry? Is the last entry positive? No, because in fact it becomes 0 for Ka equal to 3. So, we see that if Ka is less than 3, then the last entry is positive. If Ka becomes greater than 3, then the last entry will be negative, and if Ka equals 3, then the last entry will be 0. So, excluding that 0 case, which is the bad polynomial case, what about the other cases? So, when Ka is less than 3, let us look at that first. What are the signs of the entries? Plus, 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 plus. Is there any change of sign? No. So, the number of sign changes is 0. There are no sign changes. Whereas, in the other case, when Ka is greater than 3, I have plus, 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 and then minus. So, how many sign changes? No sign change in going from here to here, from here to here, but there is one sign change in going from here to here. So, for Ka greater than 3, the number of sign changes is 1. Now, this is what the original result of Routh tells you, that if you are able to complete the Routh table without any difficulty, that is, there is no singular case, you have what is called the regular case. None of the pivot elements is equal to 0, so you can go till the very end. Then look at the first column and look at the number of sign changes in the first column. The number of sign changes in the first column in this case, in the regular case, when there are no zeros encountered in the first column, in this regular case, the number of sign changes in the first column is the number of roots in the strict right half plane. That is, the number of roots with positive real part is exactly this number, the number of sign changes in the first column. And if we go back to our pole zero diagram once again, we had started sketching the root locus. We had seen that there was a part of the root locus here, there was a part of the root locus here, and the third part of the root locus was asymptotic, and the conclusion that we obtained is indeed correct, that there is at most one root which is in the right half plane, other two roots are in the left half plane, and that root which will be in the right half plane using Routh algorithm we have found out will occur when Ka is greater than 3. And so combining the root locus rules, real axis portion, asymptotes, number of branches of the root locus, those were the simplest rules, with the Routh table kind of investigation tells us that for Ka less than 3, the characteristic polynomial will have all the roots in the left half plane, and so the system will be stable. There will be no problem whatsoever. The 0 input response will go to 0 as t tends to infinity, and the 0 input response, the part of it which depends on the initial conditions of the input, also will go to 0 as t tends to infinity. However, for Ka greater than 3, there will be one root which will be strictly in the right half plane, and this case being simple, the root locus approach tells us that the root will actually be positive and real. Therefore, it will correspond to a growing exponential, and so the 0 input response could, if the initial conditions are not properly chosen, could have a term which goes to infinity as t tends to infinity. The system will be unstable, therefore the system will be bad, and this is something we do not want to happen. The case when Ka equal to 3 is the singular case of the Routh technique. In this case, of course, the answer was simple. When Ka is equal to 3, there is a root exactly at the origin. In general, when you get a singular case, the conclusion is not so simple, and as I told you, there are two singular cases with pivot element 0 but not the entire row 0, and the second case when the entire row is 0. Then there are some additional rules which enable you to proceed further and complete the table and get some conclusions about the location of the roots, but those rules are not very simple, and some of the rules which are given in some of the textbooks are not even correct. There has been discussion in the journals about the correctness of some of these rules, so let me just warn you that the methods which are given in the textbooks sometimes may not work, or they may not give you the correct answer. But essentially the problem that people have been looking at subsequently to Routh, and in fact if you remember, Routh was looking at a problem which was posed by Maxwell, which came out of his investigations, Maxwell's investigations of the governor, which was designed by James Watt and others earlier. The problem is what is called qualitative theory of polynomial root location. The complex plane can be divided into three parts: the j omega axis, the strict left half plane, and the strict right half plane. What one is looking for is a method whereby, starting with a given polynomial, without factorizing it, you would like to get some information about the root distribution. For example, from the point of view of system stability, all the polynomial roots should be in the strict left half plane, or the polynomial should be a good polynomial. So we would like to find out, knowing the polynomial, if all the roots are in the strict left half plane without factorizing the polynomial, without finding out the roots of the polynomial individually. The Routh algorithm enables you to get that information. The Routh algorithm also enables to get you the information when not all the roots lie in the left half plane. Some of them may lie on the j omega axis, some of them may lie in the right half plane. Now, just as I can find out the number of roots which are in the right half plane, they are precisely the number of sign changes. When there is no singular case, I can find out the number of roots which are precisely in the left half plane, and therefore I can find out how many roots are there on the j omega axis. And so the root distribution problem can be completely solved for a polynomial whose coefficients are all real numbers, or as one calls them, what is called a real polynomial, a polynomial with all coefficients real. It is really very surprising and a significant achievement that, at least in the case of all polynomials which have real coefficients, information about the root distribution can be obtained without factorizing the polynomial, without finding out even one root. by simply working with the coefficients of the polynomial and then using some kind of an algorithm which involves multiplication, subtraction, division of numbers, and if there is no singular case, the whole thing goes till the end, there is no problem whatsoever. There are other problems. For example, this is a root distribution into left half plane, right half plane and the j omega axis. Now, when you discuss discrete time systems, and in our course we just do not have any time to discuss discrete time systems, although I have mentioned sample data or discrete time systems in the beginning, but there is a different problem which is to be solved. There is this unit circle in the complex plane, and this unit circle or the circumference of it divides the complex plane into three parts: the part which is inside the unit circle circumference itself and the part which is outside. Now, you can ask a similar question: given a polynomial, by just working with the coefficients without solving for the roots, by doing some simple what are called rational operations on the polynomial coefficients, can I determine the root distribution? How many roots are inside the unit circle, how many on the unit circle, how many outside the unit circle? This problem can also be solved, and there are algorithms which are similar to the Routh algorithm. Techniques that are used vary from very simple ones like just the complex plane and the complex function theory, some of which you have studied, to what are called quadratic forms, which involves looking at matrices and whatnot. But that is a different deep subject, so we are not going to get into it. As far as we are concerned, when working with the root locus method, the Routh algorithm can provide us with a way of finding out if there are going to be situations where there will be intersection with the j omega axis, or at least it gives you a way of finding out whether the characteristic polynomial can become bad, and if so, for what values of the coefficient Ka the polynomial will become bad. Now, we will go back and apply this to our speed control problem with proportional control and with integral control, and check whether that system can become bad for some values of the gain, the proportional gain and the integral term gain. This we will do next time.